Hey guys, I'm Jose and this is tutorial number 21 on Cellular Automata or the game of life. So obviously if we're going to talk about Cellular Automata and game of life, we have to reference two people, Stephen Wolfram and Conaway, that basically came up with this idea or worked on this idea. Um, Extremely useful for this is Stephen Wolfram's New Kind of Science. This book explores all the rules of stellar automata. And if you're not familiar with the concept, we're going to see it now. So um, let's start defining a little bit of what we already know, and then we're going to start talking more about what a cellular automata is, okay? So we're going to work with in 3D because most of the stuff that is already in the web, it's in a 2D setup. So I'm gonna provide a 3D one that could become more instrumental for other purposes as well. So we're gonna import PCCam and Toxigeom. Right? So let's do a simple setup with a window of 600. Oh, it could be 800 by Puma P3D for now. Yeah. And we're gonna do a background black. Let's also do a little rectangle that would be in 0, 0, 600, 600, right? And we're gonna make this guy stroke white and fill something like white, but like with some transparency, something like 50% transparency, right? I'm just putting this object to have some reference of the 3D space. PCCam. Cam. So we're initializing the PCCam setup. Cam equals new PCCam is comma, right? So quite simple, very basic. Okay, there we go. Right, so we can control this plane. This is a reference plane of the world. So let's do a tab here, a new tab, and we're gonna call it CA. Right, so that's when we talk about CA. It's a short version of Cellular Automata. So let's talk about CA in general. And what our class CA is going to be, it's going to be just a node, right? It's going to be a point that will contain a state. For now, we're just going to do a point with a vector 3D that we're going to call location. Very similar to the same stuff that we've been doing before with agents and stuff. Location equal underscore location. Let's do our run function, and this guy will have a display. So void display. do a point in log.x, log.y. And this point will be white, yeah, 2.5, and it would be stroke weight quite big, right? So that's it. For now, we have a little class that is one entity, and we're gonna call this class into the canvas, right? Into our world. Reduce this a little bit. But we're gonna call it in a specific way, right? We're gonna define a grid. This is important because the CA works with a specific kind of neighborhood rule. So we're gonna use a grid. We're gonna specify first an integer, a global integer that would be cols, representing columns, and we're gonna say 100, and an integer of rows equals 100. So this is good that we have this global variable defining this stuff, so we can just change it later if we want more population or less. And we're gonna say CA, so we're calling the class, and we're gonna make an instance called grid. And this we're gonna say it's gonna be a two-dimensional array of the new type, new CA. And here we're gonna specify cols. Sorry about that. Cols, right? And rows. So what this is saying, we've seen this before. Let's do an array, two-dimensional array, where we have certain number of columns, and for each column we have certain number of rows. So that's good. Let's now initialize the class, right? So to initialize it, we need a for loop. In this case, actually a nested for loop. So for integer I equals 0, I smaller than cols, that's the number of elements that we want in X, let's say, I++. We've seen this stuff in importing and exporting data, this idea of two-dimensional arrays. So if you're not familiar with this two-dimensional array, go back to that lesson where we see that structure. So as I'm a little bit lazy, I'm going to copy this for loop. Just be sure that when you copy a for loop, in order to do a nested for loop, just change all the 3 instances of the variable I for j, and also to change cols for rows in this case, right? So we're going to specify the grid element. Grid is our, and here, so the element I, j equals new CA, and we need to provide a vector, right? pt log. pt log doesn't exist, so we're going to build it up. So we're defining a vector in the position of the point, pt, the location of the point. New vec 3D, and I'm going to say I times 10, comma j times 10, comma 0, right? This times 10 is just to make them be separated from each other. So we're going to specify, start building a grid, and each point would be in a location specified this way, right? So that's pretty straightforward as well. And the last bit of it, we're going to copy these 2 loops. We're going to put it here, and we're going to say that this guy, the grid ij, so we're going to go through every element and call the function run, right? So let's see if this is working. What are we doing? Oh, we have a problem here. We're missing a semicolon. That's good. Waiting a little bit. There we go. Okay, it's quite a big grid. But we do have the grid working, right? So now that we have this grid of points, we can, first of all, this thickness was maybe too much. I'm going to put 2. And the rectangle that we draw, it's actually not helping us at all. So we have the grid, right? That looks much better. So let's look at this grid. If we zoom in, if we really zoom in, let's look at, for instance, this point over here. This point has points around him. There are 1, 2, 3, 4, 5, 6, 7, 8 points around him, right? So the base idea of the cellular automata is the idea that this point will look around him, will see what is going on, it will check these points, and it will check if they are kind of dead or alive. We're going to do a little variable called type or state, and we're going to specify if you're alive or dead, basically white or black. And he will take some decisions based on that neighborhood, right? So if every point in the grid would take that decision, we will get some emergent behavior out of that, right? That's kind of the theory of it. So let's see how to start implementing that idea. The first thing is that point needs to know that it's part of a larger system, right? So a point needs to know not only his position, but it needs to know in where does he stand in a grid. So we're gonna say integer underscore x or integer I. This will represent not the actual position of the point, but the point, the position in the point in the grid. So it's not like a global coordinate like 200, 200. It's just like first, second, third, or something like that, right? So the first point would be the point 0, 0. And the next one would be 0, 1, 0, 2. That's in the same column. And then if we jump to this column 1, you could be in the position 1, 0, 1, 2, 3, etc. So we're going to say this, x and y equals underscore y, right? So when we build it here, we need to specify now an x and a y, right? So what is the position in which this guy was generated? Well, it was I, j. That represents literally the position in the grid. So because this is a nested for loop, the 0, 0, now the point knows that he's the first one in the grid. So we can do a little check, right? So we could say if x equals 0 and y equals 0. We're going to repeat this line here, but we're going to do it red and super big, right? So this is just for testing purposes, right? So this is if statement is saying if you are the first one in the grid, the object 0, 0, paint yourself red. And we can go through the grid specifying any element here. We know that we go to 100, right? So we could say 99. And that's the 100 element, right? The last one in the same column. So we could ask for any of the points in the area, right? So that's great. We know where we are in the grid. So let's do a function that will be called evaluate n. Make something short like that. This means evaluate neighborhood. So what would be the neighborhood? We'll see it right now. So void eval n. So the question here is like, who are we in the grid, right? If we go to the grid x and y, this is who we are in the grid, right? This is the element that we are. This instance of the class will be the element grid x and y. His neighbor, if you ask for the guy that is just on top of you, would be x minus 1, right? And the guy below you would be x plus 1. The guy to the left will be y minus 1, and the guy to the right equals y plus 1, right? Let's check this stuff, and as we did before, just to make sure that we're understanding the concept. So if x equals, in this case, 20, and y equals 20, we're going to copy this structure. We're going to do a vec3d test equals grid dot lock, right? So we know that each element in the grid, this is an instance of the class, has a location, right? And we're going to say draw the point test, again red, right? So we're specifying that guy in red, right? Well, we could say also, like, I'm going to copy that line and I'm going to say test2, right? It's going to be green, and it's going to be maybe 7 units, and I'm going to say x plus 1 to see what this is actually doing, right? So here we're going to draw the point test2 just to check what are we really talking about when we say grid plus 1. So we go, right. So x plus 1 is saying the guy to my right. And because we're just evaluating the element x20 and y20, we're getting this. If we were evaluating all of them, we will get this situation everywhere. So that would be a little bit confusing, right? And if we say minus 1 here, right, we will get the point to the left. And same thing if we put like plus 1 or minus 1 in the y, we are going to get the appropriate result, right? So in this way we're getting, we can access some trouble with my mouse. There we go. Right. So we are accessing the guy that is just diagonally. So that's a very simple way. We're not looping through every point. We're just knowing where we are, that is x and y, and asking one to the right, one to the left. There's a problem with this system. Let's say that we are in 0, 0, right? So we're in the top left corner of the screen. And we want to ask for the neighbor, right? So right now we're drawing both the green and the blue and the red points in the same position. And we want to ask for our neighbor to the left. The system will give us an error, right? We'll try to access that. And it will tell us this. No, you have an array index out of bounds exception, right? So we are asking for an element that doesn't exist. So we could, one option is just specify like tons of if statements to clean this, to say don't ask for that neighbor if you are in that position, right? But that's a little bit messy, so we're gonna do a little formula that I have here that says the following. I'm going to open parentheses. I'm going to say x plus calls, knowing that columns is the total number of columns, and then modulo calls. And I'm going to do the same thing for y plus rows, the total number of rows, modulo rows. This little formula over here, you don't need to understand it too much, but what this is saying is that you're asking for your position relative to the number of elements, and this will always give you a point. We're going to try it now. Let's say -1. If you are in the position 0, 0, your neighbor would be wrapped around the other side. Right? So this is our position, the red, right? And we are asking for the position -1, and it would be this one. So this is a way of defining that neighborhood, like through that little formula, that will be wrapping in any situation. So if we ask for a neighbor in this direction, we're gonna get the guy from below, and so forth. I mean, this is a very clean and neat way to define this, because you won't run into problems with if statements or anything like that, right? So that's great. I mean, now we have a way of asking for neighbors, all the neighbors, and get some information out of them. So we know that we are at this point. That's fine. This was for test purpose. That's gonna be out of the way. So we're gonna do the following operation. We're gonna do a variable called integer count, right? That will start in 0. And we're gonna say if, right? Something really. We're gonna do a count +1. What we need to count is, first of all, how many neighbors do we have? Right now, all of our neighbors don't have any kind of specific condition, and I actually forgot to specify that. So we're gonna do here something called an integer type, right? So all our agents will start in, means all our points will start in a state of 0, and we're gonna specify that half of them will be type 1. So we're gonna divide the population of points. Some of them will be randomly a type 0, and some of them will be randomly a type 1, representing life or death, right? So we're gonna say float R&D equals random So this is a way of doing kind of percentages. So we're going to say if R&D is smaller than 50, right? Type equals 1. We're saying 50% of the population here will become type 1. Right now we would like to visualize that as well. I mean, the type should influence something, right? So we're painting white all the points in the display. So we could say if type equals 1, that is the live condition, paint the point white, right? So let's see, I'm going to remove this line for now. This is where we're going to work, but like, let's see that that random type situation is kind of working. And that's working fine, right? So out of this grid, half of the points have been initialized with the type 1, and the rest as default are type 0. We're only drawing the type 1. So back to our evaluation function, what we want to say is like if this guy dot type, that's the variable that we were missing, right? If its type equals 1, count plus plus, right? So this is what we're saying. Get this element. In this case, we're looking at we need to specify what neighbor we are. So we're gonna say -1, -1, right? So this is going to be upper left from the position that we are in the grid. If that element is type 1, we will count. And we're going to do this for all the neighbors. How many neighbors do we have? 8. So we're going to specify 2, 3, 4, 5, 6, 7, 8. But we need to change each time the neighbors, right? So we're going to say the next one is columns nothing, and the next one is columns +1. So we're moving left, center, forward. Then we're gonna say columns nothing, rows -1. No, sorry, columns -1, rows nothing, and columns +1 and rows nothing. So this is the middle. The guy that is to my left and the guy that is to my right, and then we're gonna say columns +1, -1, rows +1, and then here we're gonna remove this guy, and all the columns will be +1, and here we should have +1 and rows +1, right? So if this little diagram, I mean, if this kind of operation is becoming a little bit confusing, draw it. Draw this kind of a grid of 3 times 3. You are in the middle, and you need to specify -1, -1 would be the upper left. The one up would be columns nothing, just as it is, and -1 in the rows. Then upper right corner would be +1 in columns, -1 in rows, and then we can build up all the possible ingredients, right? So that's great. We have our evaluation of the 8 elements around us, and we, through this little function, we don't have any exceptions, we don't have any problems with that if statement. So that's great. Now we need to, through that count that has been accumulated based on those neighbors, we can take decisions. What kind of decision can we take? We can switch something like if count is bigger than 5, type equals 0, right? So Conaway specifies a certain rules that saying like if I have too many neighbors around me, I die out of overpopulation. If I have too little neighbors around me, I die of starvation. But there's a moment, like some certain number of neighbors are kind of optimum for me, so I don't change if I'm within that condition, and I could become alive from death under some specific situation as well. But for now, like we're gonna say, what if count is bigger than 5, type equals 0. So we should be able to see at this point some change from that original kind of random grid. So we could say, I just want to check if this is working. Right, so we can see that the pattern is changing. There has been some calculations going on, and there are points that have been disappearing based on this rule. We're going to use exactly the same rule that Conaway specified. If you don't, obviously, you can look that on the internet and find what are the rules of the game of life. This is the algorithm that we're writing. It's called game of life, right? So we're going to say the following. If my type as an entity, right, equals 1 and count is smaller than 2, the type becomes 0, right? Next, that's the first rule. Like if I'm active and I count less than 2 neighbors, I die. If I'm active again, and count is smaller or equal than 3, and count bigger or equal than 2, type equals 1. The next one, it says if type equals 1 and count it's bigger than 3. So we're saying if like I'm active and I have more than 3 neighbors, I will die from starvation, from overpopulation, right? So this is the overpopulation rule. Type equals 0. This is the one that says I stay like I am. I'm type 1, I have certain number of neighbors, so I stay like that. That's kind of fine. This one is the one that kills me on overpopulation. And there's one last one that says if type equals 0 and count equals 3. So just when I am dead, right? If I'm dead and just have 3 neighbors, my type equals 1. So I can become alive. There is kind of an idea of giving birth to a new element through specific conditions. Very specific, actually, because in most cases you will count many different times, but if you are specifically 3 and you're dead, you will become alive. So we could see what is going on right now, and we will realize that we have something, but still this is not the way. Well, it's moving, right? So it's in a constant flux, looking for some point of equilibrium, right? So that's interesting. I mean, you could say, yeah, that's great, but that's not the way the game of life looks. If you have looked at the game of life, you will realize it doesn't look like this. This is a quite interesting one, I would say, still, because there's some kind of nice, very almost like labyrinth square patterns that are kind of overlapped with this more kind of organic structure. So we're going to talk a little bit about what is the difference between the game of life and how some of the most how the CAs are structured different to this one that we're writing. The problem with what we're doing is that we're going through every cell, and every cell is kind of looking at its neighbors sequentially. So the first one will look at its neighbors and change, instantly change. The next one will look at its neighbors and change. What we want to do is like, imagine that each cell will change instantaneously from looking at its neighbors. Instead of just one doing it first, the other one second, and that alters the calculation, right? So we're gonna do a little trick here. Not a trick, there's a technique. We're gonna say integer future type equals 0, right? We're gonna build up future type variable. And we're gonna do a function called update type, right? And this will say type equals future type, right? Notice that we won't put this function in the run in our run function, because we don't want to build this. We don't want to run it at the same time. What we want to do is just make each cell make this calculation, and instead of type, you build up a future type. So we'll go through all the cells, we'll calculate what will it be their future position based on the state of the grid at a given time. So we'll, as I said, we'll calculate the full grid before switching to the new type. And we're going to call this function update type from here. We're going to copy this for loop and press this. So we're going to copy it, and then we're going to run the update type. Is that the name that we gave to it? Right, update type. So this is very important because we're, as I said, we're going through all the cells, calculating how they want to be the next iteration. And then we're going through all the cells and just making that change. But if we run this now, let's see. This makes a huge difference. This is the game of life. If you've seen the game of life, or you can see it in the internet, do videos on YouTube or anything, like there's tons of experiments with this game. We can say something like 4, just for the display to be nicer. I think it's a beautiful algorithm, the way it's written, the emergent behavior, lifelike behavior that contains is extremely interesting. And again, the credit for Stephen Wolfram and Conaway for coming up with these notions. And yeah, and that should be it.